Welcome to this lecture on ballistic and quasi-ballistic electron transport, in short, nanowires. Today we're going to explore a fascinating phenomenon that challenges our classical understanding of electrical conduction. Let's start by reviewing the classical picture of electrical conduction that most of us learned first. In bulk materials, when you apply an electric field, electrons accelerate, but they don't just zoom through the material unimpeded. They constantly collide with lattice vibrations called phonons, with impurities, with defects, and with other electrons. This is the diffusive picture. Electrons take a very zigzag path through the material. They scatter many times as they drift slowly in the direction of the electric field. We define a quantity called the mean free path, denoted lambda. This is the average distance an electron travels between successive scattering events. The mean free path equals the Fermi velocity times the scattering time tau. This gives us a characteristic length scale. In typical metals at room temperature, the mean free path is roughly 10 to 100 nanometers. This means electrons scatter many times per micrometer of travel. The resistance of a material fundamentally arises from these scattering events. Each collision randomizes the electron's momentum, opposing the drift motion caused by the electric field. The classical resistance formula is R equals ρHO times L over A, where ρO is resistivity, L is length, and A is cross-sectional area. But this formula implicitly assumes that the device length L is much larger than the mean free path lambda. It assumes diffusive transport with many scattering events occurring along the length. Now here's the critical question that we're going to explore today. What happens when the device length L becomes smaller than the mean free path lambda? When L is less than lambda, we enter a completely different transport regime. If the device is shorter than the mean free path, then statistically, most electrons will cross the entire device without experiencing even a single scattering event. This is ballistic transport. This brings us to ballistic transport, which at first seems almost forbidden by our intuition about resistance. Imagine a nanowire so short that an electron injected at one end travels straight through to the other end without any scattering. The electron maintains its momentum and energy throughout the transit. At first glance, this seems to violate our fundamental expectation that materials inherently have resistance. If there's no scattering, where does the resistance come from? Here's the profound answer. In the ballistic regime, the resistance doesn't come from the channel it comes from the contacts, from how electrons are injected into and extracted from the device. This is described by the Landauer formula, which is the fundamental equation for ballistic transport. The conductance G equals G sub 0 times M times T. Let me explain each term. G sub 0 is the quantum of conductance. It equals 2 E squared over H, approximately 77.5 microsiemens. The factor of 2 comes from spin degeneracy. M is the number of conducting channels or transverse modes in the nanowire. For a very narrow wire, M might be just 1 or 2. T is the transmission probability. For perfect ballistic transport with no scattering, T equals 1. If there is some scattering, T is less than 1. For perfect ballistic transport with one channel, the conductance is quantized at exactly G sub 0. This is a fundamental quantum mechanical result. The resistance is H over 2 E squared MT, approximately 12.9 kiloohms divided by MT. This is called the contact resistance, or quantum resistance. Let me give you an analogy that makes this intuitive. Think about sprinting across a courtyard. Imagine a large, crowded courtyard filled with people. If you try to sprint across, you'll bump into many people. Your progress is slow and diffusive. This is like the classical diffusive transport regime. Now imagine the courtyard shrinks to just a tiny area, maybe 2 meters across. Even though there might be people around, the space is so small that you can sprint straight across without bumping into anyone. This is ballistic transport. But notice that even though you don't collide with anyone inside the courtyard, there's still a bottleneck at the entrance and exit. Not everyone can enter at once. This bottleneck is analogous to the contact resistance. Now let's look at how resistance depends on device length in different regimes. There are three distinct transport regimes depending on how the device length L compares to the mean free path lambda. Here's a plot of resistance versus device length. The vertical dashed line marks the mean free path lambda. For L much less than lambda, we're in the ballistic regime where resistance is constant and independent of length. In regime 1, the ballistic regime, when L is much less than lambda, the resistance is constant. It equals the contact resistance and doesn't depend on length. R equals R contact, which is H over 2 E squared M. This is the minimum possible resistance for a given number of modes. In regime 2, the quasi-ballistic regime, when L is comparable to lambda, some electrons scatter once or twice, but many still cross ballistically. Resistance starts to increase with length, but not linearly yet. In regime 3, the diffusive regime, when L is much greater than lambda, we recover the classical behavior. Resistance increases linearly with length. Each additional segment adds more scattering events. The total resistance is the contact resistance plus the classical bulk resistance ρL over A. Let me show you some visual sketches that illustrate the mean free path in different regimes. In the ballistic regime, electron trajectories through the device are essentially straight lines. The device length is shorter than the mean free path, so scattering is rare. In the quasi-ballistic regime, trajectories show a few scattering events, maybe one or two kinks, but electrons still largely maintain their forward momentum. In the diffusive regime, trajectories are highly zigzagged with many scattering events. The net displacement is much smaller than the total path length traveled. Now let's address a key conceptual question. Why does ballistic transport fundamentally defy our usual diffusive picture of conduction? The diffusive model of conduction relies on the assumption of local thermodynamic equilibrium. It assumes that at every point in the material, electrons have scattered enough times to establish a local equilibrium distribution. Ohm's law, the linear relationship between current and voltage, emerges from this equilibrium assumption. The drift velocity is proportional to the field because scattering constantly relaxes the momentum. But in ballistic transport, there is no equilibrium. Electrons are injected at one end with a certain energy and momentum distribution, and they travel through the device without scattering, maintaining their non-equilibrium distribution. The device is simply too short for scattering processes to establish equilibrium. Electrons cross before equilibrium can be achieved. Therefore, conduction in this regime is not determined by a bulk resistivity. Instead, it's determined by quantum mechanical transmission probabilities through the device. Now let's discuss how reduced dimensions affect transport. This is crucial for understanding nanowires. As the cross-sectional area of a nanowire decreases, quantum confinement becomes important. The transverse motion of electrons becomes quantized into discrete energy levels. The number of conducting modes m decreases as the wire diameter decreases. For a very thin nanowire, m can be as small as 1, meaning only one quantum channel is available for conduction. In a wide nanowire, there are many transverse modes available. Electrons can occupy many different quantum states as they propagate. In a narrow nanowire, only a few transverse modes fit. Quantum confinement suppresses most states, leaving only a small number of conducting channels. The number of modes scales as m proportional to a over lambda f squared, where a is the cross-sectional area and lambda f is the Fermi wavelength. As m decreases, the contact resistance increases because fewer channels are available to carry current. For m equals 1, the resistance is maximized at the quantum limit. Clean interfaces are absolutely critical for observing ballistic transport. Let me explain why. Interface roughness, even on the atomic scale, causes boundary scattering. If the nanowire surface is rough or contaminated, electrons scatter at the boundaries, destroying ballistic transport. A rough interface with atomic scale defects causes electrons to scatter. Each irregularity can deflect electrons, reducing the transmission probability T. A clean, atomically smooth interface allows electrons to pass without boundary scattering. This is essential for maintaining ballistic or quasi-ballistic transport. Achieving ballistic transport requires high-quality nanofabrication techniques, ultra-high vacuum conditions during growth, and often cryogenic temperatures to suppress phonon scattering. Now let's discuss coherent wave transport, which is a quantum mechanical aspect of ballistic transport. In quantum mechanics, electrons are not just particles. They are waves with a characteristic wavelength called the de Broglie wavelength. The de Broglie wavelength equals h over p, which is h over mv, where p is momentum, m is electron mass, and v is velocity. In ballistic devices shorter than the phase coherence length, electrons maintain their quantum mechanical phase as they propagate. This allows quantum interference effects to occur. Coherent transport can lead to quantum interference phenomena, such as conductance oscillations, resonances, and other effects that have no classical analog. The electron wave function can be represented as an oscillating wave. In a coherent device, this wave maintains its phase relationship as it propagates, allowing interference. However, temperature and inelastic scattering events destroy phase coherence. At higher temperatures, phonon scattering randomizes the phase, and quantum interference effects wash out. Let's do some quantitative analysis of quasi-ballistic transport. This is the intermediate regime where L is comparable to lambda. The total resistance can be split into two contributions, the contact resistance plus the channel resistance. In the quasi-ballistic regime, the channel resistance is approximately R contact times L over lambda. This is a useful interpolation formula. So the total resistance is R contact times the quantity 1 plus L over lambda. Notice how this smoothly interpolates between the ballistic and diffusive limits. When L is much less than lambda, the second term is negligible, and we recover the ballistic result, where R approximately equals R contact. When L is much greater than lambda, the second term dominates, and resistance grows linearly with L, recovering the diffusive behavior. Ballistic transport has been observed experimentally in many nanoscale systems. Let me describe some key experimental signatures. One of the most famous observations is conductance quantization in quantum point contacts. As you narrow a constriction, the conductance decreases in discrete steps of G sub 0. This plot shows conductance quantization. As you change the gate voltage to narrow the constriction, conductance drops in discrete steps. Each step corresponds to closing one quantum channel. Each step corresponds to closing one conducting mode. When m equals 4, conductance is 4 G sub 0. When m equals 3, conductance drops to 3 G sub 0, and so on. Another striking example is carbon nanotubes. When carbon nanotubes are shorter than the mean free path, their resistance is independent of length, confirming ballistic transport. These effects are typically observed at low temperatures, often below 10 Kelvin, in ultra-clean samples where phonon scattering and impurity scattering are suppressed. Now let's discuss how reduced dimensions and ballistic effects modify the resistance formula. The classical formula R equals rho HOL over A breaks down completely in the ballistic regime. Resistance is no longer proportional to length, and the concept of resistivity becomes ill-defined. Instead, we must use the Landauer-Bodecker formalism, which relates conductance to quantum mechanical transmission probabilities through the device. The conductance equals 2 E squared over H times the sum over all modes n of the transmission probability T sub n for each mode. Each conducting mode contributes independently to the total conductance. If mode n has transmission T sub n, it contributes T sub n times G sub 0 to the conductance. For perfect ballistic transmission, T sub n equals 1. For complete reflection or blocking, T sub n equals 0. Partial transmission gives intermediate values. Any scattering within the device reduces T below 1. The more scattering, the lower T becomes, increasing resistance. Ballistic transport is not just a theoretical curiosity. It has important technological implications for nanoscale devices. Modern transistors with gate lengths below 10 nanometers are approaching the ballistic or quasi-ballistic regime. This fundamentally changes how we design and model these devices. Ballistic transport can improve device performance because electrons travel faster through the channel without scattering. This can increase switching speed and reduce power dissipation. However, the contact resistance becomes the bottleneck. Engineering metal semiconductor interfaces with low resistance is extremely challenging. One-dimensional materials, like carbon nanotubes, and two-dimensional materials, like graphene nanoribbons, are particularly promising for ballistic transport because of their high carrier mobility and long mean free paths. Let me pose and answer an important question. What happens to ballistic transport at room temperature? At room temperature, phonon scattering increases dramatically. Lattice vibrations are much more energetic, and the mean free path decreases significantly. The mean free path typically decreases by a factor of 10 or more compared to cryogenic temperatures. This makes ballistic transport much harder to achieve. Only extremely short devices, typically below 5 to 10 nanometers, can remain ballistic at room temperature. Most practical devices operate in the quasi-ballistic regime. Material quality becomes even more critical at high temperature. Any additional impurity scattering or boundary scattering compounds with the phonon scattering, further degrading transport. Another key question: how do we experimentally measure and verify ballistic transport? Method 1 is length dependence measurements. Fabricate devices with different lengths but otherwise identical geometry and material. If resistance is independent of length, transport is ballistic. Method 2 is 4-terminal resistance measurements. This separates contact resistance from channel resistance, allowing you to isolate the intrinsic device behavior. Method 3 is observing conductance quantization. Discrete steps in conductance at multiples of G sub 0 are a clear signature of ballistic quantum transport. Method 4 is temperature-dependent studies. Ballistic transport should show weak temperature dependence compared to diffusive transport, which has strong temperature dependence due to phonon scattering. Let me summarize the key differences between ballistic and diffusive transport in a systematic comparison. Length dependence. In ballistic transport, resistance is independent of length. In diffusive transport, resistance grows linearly with length. Scattering events. Ballistic transport has 0 or very few scattering events. Diffusive transport has many scattering events along the length. Origin of resistance. In ballistic transport, resistance comes from the contacts. In diffusive transport, resistance comes from bulk scattering in the material. Device length requirement. Ballistic transport requires L less than lambda. Diffusive transport has L much greater than lambda. Quantum effects. Ballistic transport can show conductance quantization and interference effects. Diffusive transport is essentially classical. Temperature sensitivity. Ballistic transport has weak temperature dependence. Diffusive transport has strong temperature dependence through phonon scattering. Let's discuss the quasi-ballistic regime in more detail, which is actually the most relevant regime for many modern devices. Most practical nanoscale devices today are neither fully ballistic nor fully diffusive. They operate in the quasi-ballistic regime where L is comparable to lambda. In this regime, some fraction of electrons cross the device ballistically, while others scatter once or twice. The device behavior is a mixture of both regimes. A useful approximate formula for transmission probability in the quasi-ballistic regime is T equals lambda over lambda plus L. This smoothly interpolates between limits. This formula gives T equals 1 when L equals 0, which is perfect ballistic transport. As L goes to infinity, T goes to 0, which is the diffusive limit. Engineering ballistic transport in practical devices presents several major challenges. Challenge 1 is maintaining ultra-clean interfaces over large areas. It's difficult to fabricate devices with atomically smooth interfaces over technologically relevant dimensions. Challenge 2 is controlling doping and defects at the nanoscale. Even a few impurity atoms can significantly affect transport in a nanoscale device. Challenge 3 is forming low-resistance electrical contacts. As we've discussed, contact resistance becomes the bottleneck in ballistic devices. Engineering metal semiconductor interfaces with low resistance is extremely challenging. Challenge 4 is operating at practical temperatures. Most applications require room temperature operation, but phonon scattering at 300 Kelvin severely limits the mean free path. Let me summarize the key concepts we've covered in this lecture. Ballistic transport occurs when the device length is less than the electron mean free path. In this regime, electrons cross without scattering. The resistance in ballistic devices comes from the contacts, from how electrons are injected into and extracted from the device. Conductance is quantized in units of the quantum of conductance. G sub 0 equals 2e squared over h, approximately 77.5 microsiemens. The number of conducting modes m determines the minimum possible resistance. Narrower nanowires have fewer modes and higher minimum resistance. Clean interfaces and quantum phase coherence are essential for observing true ballistic transport. Roughness and inelastic scattering destroy these effects. Most practical nanoscale devices operate in the quasi-ballistic regime with partial scattering that must be carefully modeled. Ballistic transport fundamentally changes our understanding of electrical conduction at the nanoscale, requiring quantum mechanical treatment rather than classical models. Let me conclude with some final thoughts on the future of ballistic transport research and applications. Emerging two-dimensional materials like transition metal dichalcogenides show great promise for ballistic transport due to their atomically thin nature and high crystal quality. Topological materials with protected edge states may enable ballistic transport that is robust against disorder and defects, opening new possibilities for quantum devices. Understanding ballistic and quasi-ballistic transport is absolutely crucial for designing next-generation electronics as transistors continue to shrink below 5 nanometers. This field beautifully connects fundamental condensed matter physics and quantum mechanics with practical device engineering, requiring both theoretical understanding and experimental innovation.